Hello everyone, welcome back to Introduction to Semiconductor Devices. This is lecture 4. So in the last lecture, we were talking about how we can visualize a 2D bonding model, which shows you how silicon atoms are bonded in a lattice. And then after that, we talked about how electron hole pairs are produced by various generation processes. And in the end, we covered the differences between direct and indirect band gap semiconductors. So today, we will try to understand more about carrier properties in semiconductors. To do that, we'll start with a concept known as effective mass in the semiconductors. So we have already seen this EK diagram. This is an indirect band gap semiconductor, which is silicon. So we ask ourselves the question, how does the carrier move in a semiconductor like this? For example, if I take a case of a electron moving between two metallic plates. Let's just imagine a metallic plate with certain voltage. And then I'll apply another metallic plate. And then between them, let's say I put one of them at plus 1 volt and the other one I ground it. Okay. And now I place a electron in between that plates. So of course, the electron moves in response to the field, right? So how would you describe this? This we will describe using Newton's laws. So force is equal to mass into acceleration, and that should be equal to Q times E, right? What is the mass here we use? We use the mass of the electron, right? This is mass of the electron. I'll put it as first. All right. So this is how electron behaves in free space. But now how does it behave in a semiconductor? Okay. So let's imagine a piece of semiconductor. So I take this, I do the same thing. I ground one side. On the other side, I apply, let's say, positive 1 volt. So now the question is, how does a electron behave in this, right? How does an electron move in a semiconductor? To answer this, we need to understand what are the various forces, right, acting on the electron. So what are the types we can think of? Of course, there are, let me say, forces on an electron in semiconductor, right? I'll just make it semiconductor, semi-C. Okay. So we have first one, we have the external force, right? Which is essentially the applied electric field. In addition, we have an internal force. Force is due to the crystal, right? So let's say there are this F internal, which are essentially, electron is going to feel, the crystal potential, right? The lattice potential it will feel, and it will also undergo some scattering events, because if electron is, let's say, moving in one direction, it can undergo a scattering with a lattice site, and then it can change directions. So the forces are quite complex, for us to visualize. But let's say this F internal essentially encapsulate all of them, and we'll say that this is basically complex lattice forces, lattice or crystal, whatever you want to call it, forces. These are this F internal. So now, how does electron behave in this environment? Okay. It is going to be quite challenging if you want to monitor every single electron which is moving in a crystal. If you would like to monitor, it's going to be quite challenging. Okay, it is impossible, really. So what we will do is we will introduce a concept known as effective mass. Okay, what we'll say is just like the Newton's second law, right? F equal to ma. We will write now, basically this, both of them is F total, right? So basically F total will be equal to mass times acceleration, which is the real mass. But what we'll say is we will introduce a concept of effective mass, and we say that m star A. Okay. So basically this particular m star, which we will call as effective mass. Okay. So what does it do? This m star it's essentially capturing whatever is the effect of the crystal or lattice. Okay, all the forces and everything it will capture, and then eventually it will simply give you one number, which is going to be the proportionality between external force and how the electron, the acceleration of the electron. Okay. So M star is capturing captures effect of lattice, right? This is what it does. How can we do that, right? So the way it is done is all this, lattice potential and how electron moves in that is all captured into the EK relation. Okay. So we will use this. So we will use the, basically the goal now is how to calculate the effective mass use EK relation to calculate effective mass. Okay. This we can do because, at least qualitatively we can think about it. The EK relation is all result of how the energies are changing with momentum and all that, right, in a crystal. So EK relation we will use. How do we do that? It's fairly simple actually. Okay. So what you're seeing here is, we already mentioned that electron has a free, electron in free space has a parabolic dispersion, and we also said that when you look at a EK relation, for example here, around the edges, right, for example here, the dispersion is still parabolic. Okay, so we said these two, positive and negative K are essentially two different directions. So around the edges, band edges, be it the top of the valence band or the bottom of the conduction band, it still it can be approximated as a parabolic dispersion. Okay. So we will use the ideas that we have learned in the past. Okay. So this is just, let's say, if you have parabolic dispersion, how can we estimate the mass, effective mass from that? Okay. So let's do one thing. Let's compute dE by dK. Okay. I'll take dE by dK. If you do this, essentially it will be, I'm taking a derivative of the dispersion, so it will be h cross square K by M, right? So now you might recollect, that we know classically P is equal to mass into velocity, and we said quantum mechanically that will be h cross K, right? So if you want to define a quantum mechanical analog of velocity, what you need to do is simply say velocity should be quantum mechanically mass. Okay, so this is what you can do to define a quantum mechanical analog of velocity. So by combining, let's call this as 2, let's call this as 1. By combining 1 and 2, we can write velocity of a particle traveling in a band. Okay, if you're talking about conduction band, we're talking about electrons. If you're talking about the valence band, then we will talk about the holes. Okay, so velocity of a particle is h cross K by M, and that should be equal to 1 over h cross dE by dK. So this is fairly, simple. So what we have to do is simply take the first derivative of the EK diagram, EK relation. If you do that, you get the velocity of the particle. Okay. Once you know that, if you want to say at K equal to 0, you want to compute, then you substitute K equal to 0 and you get the velocity of the particle at the 0 point or at the edge of the band. You can get that. Okay. So this is how, we can actually calculate how carriers move in a semiconductor. We can do one more thing. We can take the second derivative. Okay. So let's try that. So d square E by dk square. Okay. It will turn out to be second derivative, so h cross square by m. Right. So now what I'll do is, I'll say, from here, I'll simply define a quantity which is called as 1 over m star. It's just 1 over m star is equal to 1 over h cross square d square E by dk square. Okay. So what this is telling you is, just a minute, sorry. Yeah. So what this is telling you is that the effect, no, we call the second derivative, inverse of the second derivative as the effective mass. Okay. That's all we have to do. Okay. So this m star, we will basically have, this is the effective mass. Okay. So if you're talking about valence band, we'll denote it as mh star. So mass of the whole, mh star, basically, effective mass of whole. If you're talking about conduction band, we'll say it is me star, which is effective mass of the electron. All right. So this is how we can simply calculate effective masses. Okay. So let me take an example. So what I'm doing here on the left is a problem from the textbook. I just picked it up, and I'll also give you a couple of more problems in the homework. Okay, you should try it out. So what you have is parabolic relations, two different semiconductors, let's say A and B, have the dispersion diagrams which are given, EK relations which are given here. So now what is the effective mass, or which one has a higher effective mass? Okay. So we have seen that effective mass is inversely related to the curvature. Okay. So higher the curvature of the band, second derivative gives you the curvature, right? So if you have higher second derivative, higher curvature, you have lower effective mass. Okay. So in that sense, if you look at this picture, you can immediately analyze that here, when you go from A to B, the curvature is increasing. So effective mass m star should reduce, right? So basically, in other words, m star of B should be less than m star of A. The reason we can say that is B has more curvature, so lesser effective mass. All right. We can also calculate exactly. This is qualitatively, you can immediately see the curvature of the bands and decide this. We can also calculate it. So here, let's say there is a dispersion relation given, and then the K is given, the number K at the edge of the band is 0.08 per angstrom, right? So we can calculate it. How do we do that? Again, simple mathematics. So basically, this is a parabolic dispersion. I mean, in general, you could write it as simply E is equal to, just a minute. I can write it as E equal to, I don't know what the coefficient is, right? But I know it is parabolic. So what I'll do is I'll simply write E minus, in generic way, I can write E minus EC equal to CK square. EC basically edge of the conduction band, okay? Sometimes these bands can be shifted. To account for that, we are doing, in this case though, in this particular case, EC is going to be 0 because conduction band minimum is at 0. This is basically EC, right here. So we don't need to worry about that. Okay. So E equal to CK square. So what is effective mass? We have to take the second derivative, right? So let's take the second derivative of this guy. D square E by dk square should be equal to how much? Second derivative, so 2C, right? So what I can do is I can combine my relations. I have this relation from here, and then I have this relation. I can combine them, and I can define basically m star as h cross square, right, divided by 2C. I think this should be fairly correct. Okay. Well, m star, it goes up, so h cross square by d square E by dk square. So that, yeah, h cross square by d. This is the relation, right? So given any dispersion, we can calculate the effective mass. All right. And one more small point I want to note before I move to the next topic. That is, when we say effective mass, right? So we know Me is basically mass of electron is 9.1 into 10 power minus 31 kgs, right? This is mass of electron. So whenever we say effective mass, many times you see that in the textbooks they refer to the ratio of m star by Me. Okay, so m star by Me is what a lot of times you see in the textbooks. Okay? So it will be some number like maybe 0.3 to 0.5, something. It can depend. These things are very much dependent on the orientation in the crystal and a lot of factors actually. Okay. So basically we just refer to the ratio. That means we are just to get the actual mass, effective mass, you have to multiply it by any. Okay? Please make sure you remember that. All right. So this is about effective mass, right?